Welcome everybody to my presentation concerning fatigue strength of Austempered ductile iron to steel dissimilar arc-welded joint according to nominal and local approaches. This is a quite new topic in the sense that dissimilar arc-welded joints are usually not covered by the present design standards. I would like to acknowledge my colleague Alberto Campagnolo, Elena Pullin, my former student, and Stefano Masaggia from Zanardi Fonderie, which supported this work. The need for dissimilar Austempered ductile iron to steel welded joints comes from the market, where possible application could be in the lifting of tractors, in quick couplers for earth-moving machinery, in a rear hub of commercial vans where the rear axle is made of steel. Then there is now a cast component to which the wheel hub is connected. Now the cast component and the bolt connection could be substituted by a unique ADI component welded to the steel axle. Another example is the side frame of bogie, where the spring housing could be welded to the steel-made side frame. With that in mind, the outline of the presentation will be first to show you the materials and the specimens preparation, specimens characterization in terms of hardness, residual stresses, and what is much important in dissimilar joints is the high misalignments that were observed. Then I will talk about the experimental fatigue tests, and I will show the results in terms of nominal stress, and I will compare with the fat classes of homogeneous steel joints reported in the standards. And then I will talk of the fatigue strength approach according to the local approach based on the strain energy density, and then I will draw some conclusions. The materials are standard S355 steel and an Austempered ductile iron grade 1050 with a tensile strength of 1100 megapascal. The isothermal heat treatment known as Austempering consisted of a heat treatment at approximately 900 degrees and then cooling in a salt bath having a constant temperature of 350 degrees. And the resulting microstructure is a circular ferrite with a retained austenite. On the left picture you see the cast iron before the Austempering heat treatment. The welding process parameters were chosen carefully in relation to the specimen thickness, which is 10 millimeters, the weld bit dimension and number of runs, the consideration of specimen distortion, where they were chosen also to prevent martensite formation and prevent crack nucleation from the heat affected zone in ADI 1050, even though, as you will see, the deburite formation was unavoidable due to the cooling condition of the ductile iron. The resulting welding process parameters, according to the suggestion of the Italian Institute of Welding, are reported in this table, and what is important is to highlight the preheat temperature, which was 200 degrees, and the interpass temperature, which was 250 degrees. The ADI plate were obtained from 12 millimeter thick plate, which were milled to the final thickness of 10 millimeters. The specimens geometry are reported here. In the first row, the butt welded joints in the partial penetration configuration, full penetration, and full penetration with the weld caps ground flush to the plate. And then we have a number of fillet welded joints with non-load carrying, load carrying, and full penetration welds. In the case of cruciform joints, the main loaded plate were in the ADI, while the attachments were in S355 material. In the case of T-joint, the main plate was in S355, and the attached plate was in ADI material. This slide reports the hardness measurement starting from the left. We see the standard ausferrite of the base material. Then we enter in the heat affected zone on the ADI. Then we encounter a peak of the Vickers hardness due to the ledeburite layer, which is a very hard and brittle phase. Then the Vickers hardness drop in the weld metal and drop again to the value of the base steel material. Residual stresses were measured through an X-ray device. Residual stresses were measured both in the X direction, the direction of the applied load, and in the transverse direction, the Z direction. We see that both in the ADI and in the steel plate materials, compressive residual stresses were measured close to the weld toe, and the values varied between around minus 100 up to minus 300 megapascals. Misalignments were also measured in terms of axial misalignment and angular misalignment, E and alpha respectively, resulting in the total misalignment delta Y. Here we report the results concerning 3 test series. We can see that in the case of full penetration but welded joints, for example, the total misalignment is limited in most cases to few tenths of a millimeter. But if we look at the cruciform no-load carrying fillet welded joints, we see that in most cases the resulting misalignment is of several millimeters. That is why we decided to change for some test series the load configuration. For example, in the case of full penetration butt welded joints, we decided to switch from the axial load configuration to the 4-point bending configuration, which is not sensitive to the misalignment conditions. While concerning, for example, the partial penetration butt welded joints, due to the misalignments, we decided to mill the specimen extremities, as you can see here, in order to reduce or eliminate the effects of the misalignments. With that in mind, we could perform axial or 4-point bending fatigue tests depending on the specimen geometry. For example, you see here a butt welded joint in the axial configuration, a butt welded joint with weld caps ground flush to the plate, again the axial consideration, and a butt welded joint or a cruciform joint in the 4-point bending configuration. In any case, we used a standard servo-hydraulic testing machine with the load test frequency between 10 and 30 Hz and a nominal load ratio in most cases of 0.05, and some tests were performed also at 0.5 load ratio for comparison purposes. The failure criterion was the complete specimen separation, and the runout was established at 2 million cycles. A survey of damage analysis is reported in this slide, starting from the butt welded joints with partial penetration. We observe the crack initiation at the interface or at the weld root with crack propagation through the weld throat. Concerning butt welded joints with full penetration, we observe the initiation at the weld toe and propagation through the main ADI plate. In the case of butt welded joints with weld caps ground flush to the plate, we observe the crack initiation and propagation through the interface. According to these pictures, you see that the crack initiation is in the ledeburite phase, and then propagation is in the ausferrite. Going to the fillet welded joints, we observed always crack initiation at the weld toe in the ADI plate and the propagation normal to the stress flow in the ADI plate. Crack initiation again was in the ledeburite and then propagation in the ausferrite decomposed. I want to show now the results in terms of nominal stress and the comparison with the FAT classes and fatigue curves reported in the design standards or recommendation. As a general comment, you see that in cases of all butt weld joints, the fatigue strength at 2 million cycles is higher than that reported for homogeneous steel joints in the IIW recommendation or Eurocode 3. It should be noted that in the case of partial penetration butt joints, the nominal stress is referred to the weld throat area according to the recommendations. The second remark is that in the case of ground butt welded joints, the slope is very, very shallow. It is around 28. So the fatigue strength at 2 million cycles is higher than the corresponding FAT class for homogeneous joint, but in the medium and low cycle fatigue, we have a much lower fatigue. Similar considerations for fillet welded joints. The fatigue strength at 2 million cycles evaluated for a survival probability of 97.7 is higher than the FAT class reported in the IIW recommendations or Eurocode 3, except for the case of full penetration K joints, for which the FAT class of hybrid joint is more or less the same as reported in the IIW recommendation. Again, due to the much shallower slope with respect to the typical value of 3 valid for homogeneous steel welded joints, the fatigue strength in the finite life region is often lower than the fatigue curve reported in the design standards. This is a summary of all results relevant to weld toe failure only on the ADI side in order to present homogeneous data in terms of fatigue damage. You see that in terms of nominal stress, the data are present a very high scatter. The scatter index between the 2.3 and 87.7 survival probability curves being of 5. This is due to the different stress concentration effects we have, and that is why we wanted to apply a local approach in order to correlate the different stress concentration effects. To deal with a local approach, we choose the averaged strain energy density approach proposed by Professor Lazzarin at the University of Padua. According to this approach, the fatigue strength can be expressed in terms of a damage parameter, which is the strain energy density, delta W, evaluated inside a structural volume surrounding the critical points. The critical points are typically the weld root or the weld toe in fatigue of welded joints. The shape of the structural volume was assumed to be simply a circular sector having radius R0. So if we know the local linear elastic stresses in terms of notch stress intensity factor, we can immediately write the strain energy density once we know the radius R0, where the structural volume, where the stresses must be averaged. E is the elastic modulus, and E1 is a known parameter which depends on the notch opening angle. Now, the problem is how to evaluate R0 for ADI to steel hybrid joints, since the R0 values are known only for homogeneous joints in structural steels or aluminum alloys. In order to calibrate R0 for ADI to steel dissimilar welded joints, we considered the joints exhibiting weld toe failure. So we took the results of fillet welded joints where we have the main plate in ADI materials, and we plotted the results in terms of notch stress intensity factor, and we obtained the characteristic value at 50% survival probability at 2 million cycles. Then, on the other hand, we had the plain welded specimen, which is the ground butt joints, and we considered again the fatigue strength at 2 million cycles. Then, according to the strain energy density approach, at 2 million cycles, the strain energy of the two cases must be the same. This equation has a unique unknown, the size of the structural volume. So, performing the calculation, the result was 0.53 millimeters. So, using the value of R0 equal to 0.53 millimeters, all results relevant to weld toe failure were elaborated and presented again in terms of strain energy density, which indeed was converted into an equivalent uniaxial stress state. So delta sigma equivalent peak is nothing but the strain energy density at the critical point reconverted into an equivalent uniaxial stress state. So you see all results which are now correlated by a much narrower scatter band. The scatter index is 2.7. You can remember that the previous one in terms of nominal stress was double. It was around 5. And what it is interesting is to compare the 97.7 survival probability curve of hybrid joint with the same curve valid for welded steel joints. You can see that the high cycle fatigue strength is more or less the same, but the slope of the hybrid joint is much shallower, so the fatigue strength in the finite life region is much lower. For example, at 100,000 cycles, the fatigue strength of a hybrid joint is half that of homogeneous steel welded joints. So, summarizing the main conclusions, we tested the Austempered ductile irons to steel dissimilar arc-welded joints. There is a brittle phase, the deborite, which is unavoidable on the ADI side where crack initiation starts. However, the endurable stresses at 2 million cycles for hybrid joints are higher than those reported in the design standards for homogeneous steel joints. Then we applied the local approach and we estimated the size of the structural volume. But what is most important for practical application is that the fatigue strength in terms of local stress at 2 million cycles is more or less the same than the homogeneous steel joints. But since the slope of the fatigue curve is much shallower, in the finite life region, the fatigue strength is progressively lower than the one of homogeneous steel joints as we approach the low cycle fatigue regime. So thank you very much for your kind attention.